Now that we've seen how a stable fixed point gives rise to a 2-cycle, which gives rise to a 4-cycle, we see that there's an incredible rich zoo of phenomenology that can occur. Let me now briefly summarize it. So let's plot a fixed point value as a function of the control parameter a. So again, what we're doing is we start with some initial value x, we iterate a long period of time, and either we're going to settle into a stable cycle or we're going to settle into something else. And what I'm plotting here is the value of x's that are actually obtained when I throw away some early time transients so that the dynamical system has settled down into its long time behavior. And so what we've seen, first of all, is that there was a transition at 3. Below 3, we have a single fixed point. And then at 3, there was a pitchfork bifurcation, or what we might call a period doubling bifurcation. This behavior between 3 down to 1 of a single fixed point, that single fixed point was born by a transcritical bifurcation at a equals 1. In a similar way, each of the 2 cycles gives birth to another set of period doubling bifurcations. So there's another critical point, which turns out to be at roughly 3.46 ... But then each one of these period 4s give rise to its own period doubling bifurcation. This continues ad infinitum until there is an accumulation point of these period doubling bifurcations at a value of a, which is of the order of 3.570. Then between 3.57 and 3.67, there is a noisy regime. At 3.67, something magical happens, which is that the first odd cycle appears. We've seen that the period doubling bifurcation was a natural way of having cycles with even numbers of fixed points, but an odd cycle appears at 3.67. And at 3.8284, which turns out to be equal to 1 plus the square root of 8, something really magical happens, which is that a 3-cycle appears for the first time. So this 3-cycle is 3 points, and each one of these points along the 3-cycle has its own set of period doubling bifurcations, which continue at an accumulation point, and this goes on ad infinitum. And finally, at a equals 4, which is the last point where this map is actually well defined, right at this point, this is a poor man's random number generator. So if we're thinking of this as a model for the number of bugs in one year as a function of the number of bugs in the previous year, when a is equal to 4, this is just a pure random number generator. Now, one more thing which is I'd like to just point out about this bifurcation sequence is that, as I mentioned, going from a 1-cycle to a 2-cycle, and then 2 to a 4 and 4 to an 8, each one of these period doubling bifurcations is basically the same phenomenon happening at a smaller scale. So in fact, the windows of stability of each of the cycles, so let's call L2 to the 1 is the width of the 2-cycle. Then there's another window here, L2 to the 2, the width of the 4-cycle. And then there's a L2 to the 3, the width of the 8-cycle, and so on. L2n, the width of the 2 to the n cycles, goes down exponentially as delta to the power n, where delta is a universal number, 4.6692 ... And what I mean by universal number is that this behavior happens for any nonlinear map which has a single quadratic maximum. So the crucial point is what happens near the maximum itself essentially determines all of the dynamics, and we have a universal behavior for the sequence of period doubling bifurcations. To summarize, this is an extremely rich dynamical system that arises from very simple rules.